Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Lexicographical numbers, Leetcode 386. In this problem, we are given an integer n and we should return all the numbers in the range 1 to n sorted in lexicographical order. And we must write an algorithm that runs in O of n time and uses O of 1 extra space. Lexicographical ordering is similar to dictionary order. When we sort the words lexicographically, what we mean is we should compare them character by character from left to right. And in case of numbers, it will be digits by digits. For example, if we have the words apple, banana, and cherry, then the lexicographical ordering will be 1 for apple, 2 for banana, and 3 for cherry. Because character A is more than B and character B is more than C. Similarly, for given number n, when we generate all the numbers, the lexicographical ordering is 1, 10, 11, 12, 13, then 2, 3, 4, 5, 6, 7, 8, and 9. So we start with 1, then comes in 10 because 1 is more than 2 here, and 10 comes after 1 because it is longer than 1. Then comes in 11, 12, 13 because they are lexicographically smaller because 0 is less than 1, then 1 is less than 2, and so on. So this is how we define the lexicographical ordering. Now in terms of solution, one of the naive approach can be that we loop through the numbers 1 to n and convert each number to string and sort the strings, and strings actually sort lexicographically, and we convert the sorted string back to numbers. But because of the sorting algorithm, the time complexity will be O of n log n. And in this solution, we want the time complexity to be O of n. So that means sorting is out of the window. So then let's look at the number generation a bit closely. So first we want numbers starting from 1. That is, from 1 we go to 10, then we go to 100, then we go to 1000, and so on. Then we start all the numbers starting from 2. For example, 2, 20, 200, and so on. So in a way, this gives the picture of like a depth first search where we recursively go deeper in the tree when we multiply current number by 10. And if at any time number becomes larger than n, then we should backtrack and try to explore its siblings. Let's take n or number as 133 and we start from 1 and add it to our result. Let's call it answer. So we are doing DFS in the pre-order manner. That is, we process the parent node first and then the child node. So here we processed 1 and add it to our answer. Then we go to its child by multiplying by 10. Then we see 10, we add it to the result. Then we go deeper again. We go to 100 and we add it to our answer. Then we further go deeper. This time we will get 1000, and this time we have to backtrack because 1000 is more than 133. And then we come back to 100. We have already processed 100, right? So now we backtrack to 10. So now we will go to its siblings. At any point, there will be 10 siblings at each level for a number. For example, for 10, we have numbers from 100 to 109. Similarly, for 11, it is 110 to 119, and so on. So we backtrack to 10. The next child for it is 101. So it adds 101 to the answer. Then it tries to go deeper, but again 1010 is more than 133. So we backtrack. 101 is processed now. So now we try to go to its siblings. So we go to 10, then we go to 102, add it to the result, and so on. So now we have processed all the numbers starting from 10. We will do the same thing for all the numbers starting from 11. So we backtrack to 1, then the next child for it is 11. We add 11 to our answer and then go deeper and find all its children. So we find all the numbers starting from 11. So we get 110, 111, all the way up till 119. Then we backtrack and come to 1 again. From there we come to 12, add 12 to the answer. And then we go deeper and add all the numbers starting from 12 to the answer. So it will be 120 to 129. Then we backtrack and come to 13 and we add 13 to our answer. And then we go to its children and add the numbers from 130 to 133 to our answer. Because as soon as we go to 134, we need to backtrack because 134 is more than 133. So now we have processed all the children of 13. We backtrack and go to 14 and add all the numbers from 14 to 19 to our answer. So now all the numbers starting from 1 have been processed. Then we go to 2. Similarly, we will start adding all the numbers starting from 2. So we will add 2, 20, 21, and so on. Similarly for 3 and all the way up till 9 and add all the numbers. So this is how the whole DFS will work. And just one point of difference in the DFS. So if you notice, except for the first level, all the levels have 10 siblings at maximum. So for example, here we can start from 10 up till 19. Similarly, here we start from 100 and go up till 109. But on the first level, we don't have a DFS starting from 0. because problem demands that that number starts from 1. So in this level only, we have 9 siblings instead of 10. So now that we have covered the DFS logic, let's see how we can code it. So we start by creating an empty list answer to store all the numbers in a lexicographical order. And we can pass in the capacity as n because that can do a slight optimization in Java. Now we will start the DFS from the first level. So remember, we have to start from I equal to 1 till I less than 9 because on first level we have 9 siblings. And let's call our DFS function. We will pass our current number. We will also pass the maximum value we want or the target number and answer so that DFS can fill in these answers in the right order. And finally, we will return our answer. Now let's write our DFS function, which is more important. So we just need DFS to fill our answer, so we don't have to return anything. This will be our current number. It takes the target number or the maximum number that we can go till and the list of answers. So what is our base condition? It is when our current number is more than n, then we should return. Otherwise, we will add current to our answer. So that's what we meant by pre-order traversal. And now we will start the DFS again. So it will have 10 siblings at each level. So we will just start from I equal to 0 till 10. And before doing a DFS, we can check if the child is more than n, then we can backtrack. Of course, it's not a necessary condition because we are already checking if current is more than n on line number 12 itself. But this step can do a slight optimization, but also adds an extra if condition. So it's up to you. And what will be the child? So for going deeper, we will do 10 into current and we will do plus I to get all the siblings. Otherwise, we will go deeper. So we will just pass in the next number as current. So it will be 10 into current plus I and we'll pass in n and answer as always. That's it. And now let's run this code. Let's submit this code. Cool, it beats 100%, but again, we don't trust these numbers. In terms of time complexity, it will be O of n because we are going through each number only once and then we are adding it to our answer. And in terms of space complexity, it will be O of log 10n because at each level, our DFS is breaking into 10 paths. So the length of the recursion stack will be O of log 10n. And in this problem, it was said that we should have only extra O1 space. So this kind of breaks that rule, but still it's an accepted answer. By the way, this is still proportional to our answer requirement of O of n. But if the interviewer doesn't agrees with it and he said that no, he wants O of 1 extra space solution, then that's bad luck. But actually there is also a solution which is not very hard, but I still prefer DFS given the simplicity of the logic. So now let's see the iterative solution which actually takes just O of 1 space and still solves this problem in O of n time. For that, let's look at the recursion tree again. And this time, instead of calculating the numbers up till 133, let's try to calculate it till 233. I think one of the iterative approaches could have been that we could have used stack, but that again would have required extra memory to store all the DFS state and would have been more complicated to implement as well. But do we really need to use the stack? Let's look at the pattern more closely. So when we are going down, we are actually just multiplying the number by 10. So we started from 1, then we go to 10, then we come to 100, and then we get 1000. And because 1000 is more than 233, so we have to backtrack. So that means instead of backtracking now, we don't even go there. So we always check if our current number is less than the given number, then only we go down by multiplying the number by 10. For example, for 233, we came to 1, we added to the answer, then we come to 10, added to the answer, then we come to 100, we again added to the answer, and then the next number is 1000, so we can't go there. Now we can't go deeper, then what should we do? We should start processing the siblings. So we will start adding 1 to the number, so we will go to 101, 102, and so on. But at every point, we have to check if the sibling value is now more than the given n, then again we should backtrack. And how do we backtrack? We just divide it by 10, right? So for example, instead of 233, we were given 108. Then as soon as we come to 108, we then try to go to 109. But as soon as we add 1 to it, we already know that we cannot move forward. So we divide back and get 10 again. And then we will again start going to its sibling. So again, we will add plus 1 to it. So it will become 11. Now for 108, of course, we can't go deeper because the next number will be 110, which is more. So we will go to 11, 12, 13, and so on. But if it was 233, then we would have gone down. We would have gone to 110, 111, and so on. So this one is easy. So just to go one level higher, we have to divide by 10, and to go one level down, we have to just multiply by 10. But in the recursion tree, we have 110 under 11. So that means we should also go up when the last digit of the current number is 9. For example, if we have reached 109, so then what will be the next number? It should be 110. But this tree should always contain the value starting with 10. So this does not belong here. And also 110 will be printed before 11, which is wrong. So we again divide this number by 10, which will take one level higher. But now the parent will be 11 instead of 10. So this way we came to the sibling of 10, that is 11. So again we will process it. Then we will again multiply by 10. We go to its children. So we will get 110, 111 and so on. And so we again come to 120 now. And as now 120 is divisible by 10, we again come one level higher to 12. We will go higher. And this logic continues. So far so good. But we still have one case remaining. And that's why I took this number 233. And suppose now we have generated the number till 199, and now we do plus 1 and then divide by 10. So we will come to 20, which is a wrong order because we have skipped number 2, and number 20 should come after 2. So we should get 2, 20, 200 and so on. So when the number is divisible by 10, we should continue to divide this number until it is divisible by 10. So for example, when we went from 110 to 11, that worked because there was only one zero at the end of 110. But in this case, we have come to 200 and it has two zeros at the end of it. So we have to now skip to the grandparent. And because of this logic, we have to actually use a loop to continue dividing this number by 10. Because now this was the last number for 1, which we had to process for 233 at least, right? So we will come back to 2, and now we will again go down by multiplying by 10 and come to 20. Then we will come to 200, and this time 200 is in the correct order. So now let's jump into the code part. So because this logic is very similar to DFS, I will try to reuse as much as possible from the previous code. So we'll reuse the answer list, and instead of going from 1 till 10, we will just go till n now and keep on adding the number to our answer list. Let's define our current number instead of passing it to the DFS, and initially it will be equal to 1. So we will add current to our answer. Now we will try to go to its children similar to DFS. So we will check if current into 10 is less than equal to n, then we will just multiply it by 10 and it will be added to our answer in the next iteration. So then next time we will, for example, we start with 1, then next time we will get 10, then next time we will get 100 and so on, like for 233. Otherwise, we go to its siblings just by adding integer 1 to it. But before that, we should check if current is already greater than equal to n. That means we should go one level higher, like we saw for 108. Now we go to the sibling. But if at any point this number now becomes divisible by 10, then we should run it in the loop like we saw for 200 or 109, and then we will just divide it by 10. And finally, we will return our answer. So hopefully that's it. Now let's try to run this code. Let's submit this code. Cool. In terms of time complexity, it is still O of n because we are just running through this loop and processing each number only once. And in terms of space complexity, it will be O of n because we are returning this answer list. But now our auxiliary space complexity is O of 1 because we are not using any extra space or data structures, but some variables here and there. But that just takes constant space. So that's it. Apologies for voice drops sometime because I have some sore throat. I hope this video was useful to you. If it was, please like, share and subscribe. The code link is in the description below. If you have any questions or suggestions, please write them in the comment box. Thank you for watching. See you next time.